Welcome. In this video I'll discuss the ITG instability. This is the ion temperature gradient, and it's a kinetic instability which is driven by gradients, so radial gradients in the ion temperature. And it's an important instability for transport in modern high temperature tokamaks. Usually it's modelled with gyrokinetics or gyrofluid models, but it can also be captured in some way by extended fluid models. And so here I'll first discuss a simple picture of what the instability looks like, and then I'll show the equations you need to capture it, discuss a bit some of the important features of this. So one particularly important topic is the gyroviscous cancellation, and this appears in many extended fluid or MHD models. I won't be able to go through the full derivation because it's quite long, but I'll show you how the dispersion relation comes about and show how the thresholds come about. So there's a threshold which appears in the gradient, and so the mode is stable up to a critical gradient in the temperature gradient, and then above that gradient it becomes unstable. And so this is thought to be one of the reasons why transport in tokamaks is so stiff, because if your gradient goes above a critical level, the instabilities suddenly appear and push the gradient back to that critical level. Now there's a nice paper which I'm basing a lot of this on, which is this Dalton-Schnack's paper from 2011, and this is reference up here. But it doesn't contain the particle picture model that I'll discuss first. So first we'll go through a simple particle picture. What this relies on is two main ingredients. So one is the drift, so gradby or curvature drift of the ions when you have a gradient of magnetic field, and the other is the adiabatic response of the electrons. And so first we'll consider a case where we have the magnetic field coming out towards us. So this is the B field here, and we've got gradients of B this way, so high magnetic fields on the left, low magnetic fields on the right, and so this could be like a poloidal cross-section of a tokamak with the radius going outwards to the right. And now we have ion orbits and ion drifts, and these will orbit so that they go downwards, and so the ion orbits will look a bit like this. So large orbits here, small orbits on the left hand side, and so as an ion orbits around the field line, it gradually drifts downwards, and so there's an ion drift which is downwards, and this depends on the thermal speed of the particle. So this drift is approximately equal to 1 over the radius of curvature and the ion cyclotron frequency. So this radius of curvature is determining the gradients of this B, so that's the major radius, and then it depends on the perpendicular speed is the grad B component, so that's the grad B part of the drift, and then the parallel speed, which is the curvature drive part. So this is like grad B, and this is the curvature. Both these contribute the same amount if it's isothermal, well, if the temperature in the perpendicular and parallel directions is the same. So there's this ion drift, and importantly, because it depends on the speed, it depends on the temperature. So this is proportional to the ion temperature. And now if you imagine having a perturbation where so we start out with flux surfaces like this, and then we have a perturbation which pushes flux surfaces out and inwards, and so we end up with contours of constant temperature looking a bit like this. And so now if we look here in the vertical direction where the drift is, so here we have high temperature. Yes, this is high temperature, and this is low temperature here. And now what's happening here is that the ions, if they're hot, have a faster drift, and if they're cold, they have a smaller drift. And so at this point, the ions are drifting faster here than they are there, and again they'll be faster here. So at this point, drifting quickly again. And so what we end up with is essentially these ions piling up onto these ions, so we end up with a high density. So n is increasing here, And at this point here we have slow ions, and then this point is moving quickly, so here we have density decreasing. So the differences in temperature give us differences in density, and then the electrons respond along field lines. And this gives us a relationship between the change in density over the background density with the change in potential, delta phi over the temperature. It's the electron temperature. And this determines and says that where we have density increasing, the potential also increases. And so this gives that delta phi also increases. And so here delta phi decreases. And so this point here we have electric fields, so we have gradients in potential, so potential is increased here and decreased there. And so the potential, we'll use a different symbol, so the electric field, so like this, and at this point the electric field is going up. So here the electric field is going up from the high density to the low density. And now these electric fields, of course, now interact with the magnetic field, which is coming out of the page, and these produce drifts, which are, so in this case it's inwards. So we have I'll draw over here. So essentially it reinforces this original flow. So we have an E cross B drift, which is E cross B, and E cross B drift here is to the left. E cross B is there, and E cross B drift is in that direction. And so these drifts now enhance the original perturbation, and so we have an instability. So in summary, we have a temperature perturbation. It gives rise to a difference in the drift velocity, and that difference in drift velocity gives us density perturbations, and those density perturbations give us potential perturbations through the Boltzmann relation. Those potential perturbations give electric fields, and those electric fields give E cross P velocities, which enhance the original perturbation. And so that cycle continues, and these perturbations get bigger and bigger, and so they grow into an instability. Now, in this simple picture, we haven't really used the parallel dynamics at all, except for the electrons along the field lines. In 3D, this interacts with the ion sound wave as well, and so that below a critical gradient, this is just the sound wave, but above the critical gradient, it becomes unstable. And so once you include the parallel dynamics, you end up with a threshold, and so there's a critical temperature gradient. Now to see this or derive this in a fluid model, I'll start by writing down the equations we need. So we have the typical conservation equations for the particles. So we have the continuity equation for the density, it's just the standard divergence of n times u. We have the momentum equation, where pi here is the ion viscous tensor. We'll come back to that very shortly. We have the ion pressure equation. Here's the ion pressure equation. So we have gamma is just the ratio of specific heats. So gamma is just 5/3 here. Q is the heat flux, which again we'll come back to very shortly. And then we have the electron pressure as well. So far this is fairly standard, but it turns out these are actually quite crucial to this instability. If you have just an ideal MHD or resistive MHD or even Hall MHD, then this ITG mode is stable. What it needs are these FLR effects, so finite Lama radius effects. Let's say so resistive or Hall MHD is not enough to get these instabilities. And there's these terms here for the stress tensor and the heat flux need to include terms which depend on the ion gyro motion. Now in plasmas, if you have ions moving on their orbits, so ions going on in orbits like this, you might have, say, differences in temperature give you different orbit sizes. For example, so you have a bunch of different ions on orbits. what happens is that you can end up with the flows which look like flows in a fluid picture, but actually don't correspond to anything moving. So if you have ions like in an orbit like this, and then we take like a volume of fluid, it will appear in this region that there's a net motion downwards. It's like a fluid flow downwards because the ions here are moving faster than they are here. So the fluid velocity is down, but actually there's no advection. There's nothing moving anywhere because ions are just going around in orbits, and so there's a fluid flow. So diamagnetic flow. It's called UI star, which is the diamagnetic. And this corresponds to a flow which is just due to ions going around in orbits, and actually doesn't result in any net motion of the plasma. And so what these extra terms do is essentially partially or fully cancel this motion here. And so this stress tensor here has a component which comes from this diamagnetic flow. There's a component of the stress tensor called gyroviscous stress, which is just due to the ions going around on their orbits, and doesn't need any collisions to give any kind of viscosity. And so this is just given by B cross grad ion pressure, E and B, the ion diamagnetic flow. And so it's just due to pressure gradients, so either differences in temperature causing apparent motion or differences in density. So if there are more ions on this side than on that side, again it will appear like there is a net flow. And so there are components. So pi GV is a gyroviscous, and so although it appears like a viscosity, it's really just ions going around on their orbits. And so what's often assumed is that this viscosity effect cancels with the advection due to this diamagnetic flow. And so what's often done is we assume, so this is actually not completely true. It actually only cancels out about half, but most of the time it's sufficient, and this is actually quite widely used in many different models. This is called the gyroviscous cancellation. And so in the momentum equation, so this d by dt, this contains, so here this d by dt, so this is obviously partial by dt plus u dot grad term here, and now this u contains both things like the E cross B advection velocity, but also the diamagnetic flow velocity. And so what the diamagnetic cancellation does is partially cancel this with the diamagnetic flow part of this. And there's a similar cancellation in this term here. So here this is the same expansion convective derivative, and there's a cancellation between part of this and this term here. So the heat, or the heat flux also due to ions going around in circles. So in the same way that there's apparent velocity, there's also an apparent heat flux, but this just cancels out. So including models for the gyroviscous temperature and the gyroviscous stress is one way of doing this. The other way is to evolve separately. Essentially, when you have these advective derivatives, you subtract out the diamagnetic contribution to this velocity. And so these advection terms don't include the diamagnetic flow component. That's usually an easier way of doing this. So you replace this u with a u minus diamagnetic flow, and cancel that out with this term here. And so similar for the ion gyroviscous heat flux, you just cancel this with the the diamagnetic flow component in this advection. And so if you've done this, you can work through the dispersion relation. Say there's a paper that does this. You can go through the paper and see in more detail. So where these terms, so it's a cubic equation in the frequency. So omega is the frequency, angular frequency. This is basically the sound wave. So it's like k parallel times the sound speed. This is like the electron, so it's the sound speed with the electron temperature in, and then this term here, the omega star Ti, is the component which depends on the gradients of the ion temperature. So this is so this looks a bit like an drift velocity of 1 over b and a charge and a gradient, but it's coming about from a different way. So it's like the electron drift wave has the diametric, so the drift frequencies in it, but they come about from a different form. If the ion temperature gradient is small, so if this term here is small, then what we end up with is essentially that these two terms are 0. So if this term is ignorable, then either omega is 0 or these two are equal. And so you just get that omega squared is the sound speed or sound frequency. So this becomes a sound wave. As the temperature gradients increase, so this term becomes larger. The frequency at large frequencies, we can make some simplifications if we assume that this frequency is larger than this. So if the frequency is higher than the sound wave frequency, then what we end up with is we can ignore this term here, so we end up here with an omega cubed, and here we can move this to right hand side, and we get a term, an expression for the cube of the frequency and the in terms of the temperature gradient. And so this temperature gradient is often replaced by eta, so eta I times the ion temperature, and so hence it's also known as the eta I mode. Now eta I is basically a measure of the gradient, so it's 1 over the length scale. Because this is a cubic, one of the roots of this has an imaginary component, and it has a growth rate, and so the growth rate is therefore like the cube root of eta. So eta I to the 1/3, where this eta I measuring the gradient of the ion temperature. And so what you find is that below a critical ion temperature, where the ion temperature gradient term is small, you just get sound wave. Above the ion temperature gradient critical threshold, you end up with a growth rate which depends on the cube root of the ion temperature gradient. So the growth rates, the imaginary components of the frequency. If this is like the modulus of, or let's say eta I. So below a critical value, it's 0. So here it's stable, and it's just the sound wave. And then above this critical gradient threshold, it ends up doing something like this, and this goes like the cube. So the cube root of the ion temperature gradient. And so you have a fast growing mode above this threshold. So this is an important critical threshold for transport in tokamaks.